All right, so as I mentioned just a moment ago, there is a homework set number 15 on listed on your Canvas page. I had every intention at the beginning of this quarter to create a homework set having to deal with filter circuits. Just to give you guys a little bit more practice, I am running out of steam, so that homework set is not going to exist. So I will wind up just deleting that due date and all of that kind of stuff off of Canvas. So obviously that won't in any way, shape, or form impact your grade. So let's talk very briefly about where you should expect to see filters regarded on material for the class or whatever. There is going to be a problem on your test on Friday. It's the bonus problem that will be related to filters. My expectation there is for you to be able to give me just the simple transfer function, okay? So I'm not expecting you to take that 5 steps further and give me the magnitude of the frequency response or the phase of the frequency response, anything like that. Just literally apply the voltage divider rules and give me the transfer function of the either first or second order circuit that I give you. So I'm telling you that should effectively be a free 5 points. It should be very, very simple. Outside of that, there will be a design project associated with filters. I'm going to ask you to design second order filters for a couple of specific applications. Realistically, it should be extremely straightforward. There's a distinct possibility that in the video that I asked you guys to watch, I literally worked one of the design problems that I'm expecting you guys to do. So did I show you in that video using L2 Spice and putting a whole bunch of points per decade to make sure that everything's smooth and all that kind of stuff? Okay, yeah. Good deal. So that is my expectation of you guys' knowledge and ability to practice with filters. For this class, when we get to circuits 3, we'll spend a lot more time going over higher order filters and all of that kind of good stuff. So if I'm being honest, this is just something that I threw into circuits 2 because I think it's interesting. Was never really part of the class until I started doing this. So, okay. So if the video that I had you guys watch covered band pass and band stop filters, then today I want to look at second order high pass and low pass filters, and then that'll be the material. Okay. So let's look at a second order low pass filter first. So I'm going to ask you guys a kind of conceptual question here. Should be fairly obvious from all of the other filters that we've looked at or I've had you look at, that we are effectively just using an RLC network as a voltage divider for these simple passive filters. So if I want a low pass filter response, what element do you think I should be taking the voltage drop over in order to generate a second order low pass filter? The capacitor, absolutely. Pretty simple and straightforward, right? So in the frequency domain, our circuit would look something like this. Here's our input voltage as a function of frequency, our resistor, the impedance of our inductor, Jonathan's talking about baseball too loudly. Jonathan, be quiet. Oh, well, son of a bitch. All right, so this is our circuit. So as, let's call it practice for the exam, I want you guys to tell me what our transfer function should be. So, oh, go for it.
Whenever J giving a C.
You're killing, okay, there you go.
Yeah.
Killing me with W's. It's definitely an omega.
Yeah. Over, R plus, J omega L, plus whatever J omega C.
Absolutely. You would have gotten 5 points on your test for that.
Sure.
That is literally all that I'm asking you guys to do for the test with regards to filter circuits. You can, if you're feeling squirrely and have the time, simplify it further, which we're going to do here in just a moment, but I am not in any way, shape, or form expecting that of you, okay? So in order to simplify this, in order to make it more easily split into its constituent real and imaginary parts, I am going to multiply through by a factor of j omega c over j omega c. And when I do that, obviously I'm just going to have a 1 in my numerator. And then let's talk about what's going to happen in our denominator. So it should be fairly obvious that j omega c multiplied by r is going to be where the imaginary part of my denominator comes from. So I'm going to have j omega rc over here, and that is a positive term. For the other bits, so I have a j times a j, right? So that's going to look like -1, j squared is -1. So I'm going to have -1 omega squared LC, and then I'm going to have a +1. So I'm going to write this as 1 minus omega squared LC, like so. And now to continue splitting this into its real and imaginary parts, what would I do? As a hint, it's the exact same thing that we did on last Friday and all of the examples that you watched in the video. It's not the multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. Absolutely right. So that's going to look like 1 minus omega squared LC minus j omega RC over 1 minus omega squared LC minus j omega RC. And obviously then my numerator is just going to be 1 minus omega squared LC. That's my real part. My imaginary part is going to be negative j times omega RC. And then what should my denominator be for both of these terms? And it's going to be the same thing.
Uh, 1 minus omega squared LC squared.
So 1 minus omega squared LC quantity squared. Okay, I agree with that.
And then, minus J omega RC squared
I disagree with that.
plus J omega RC.
I agree with that. Omega RC squared. Yep. So j times negative j is -1, which is +1. Absolutely. So it should literally always be the real part squared plus the imaginary part squared. All right, so we have things split into the constituent real and imaginary parts. So now we can very easily find the magnitude response. So that's going to be the square root of the real part squared plus the imaginary part squared. So we're going to have 1 minus omega squared LC over 1 minus omega squared LC quantity squared plus omega RC quantity squared. And then square that. Once again, I'm just neglecting the negative sign here because I'm squaring it, it's not going to matter anyway. So plus omega RC over 1 minus omega squared LC squared plus omega RC squared. Close my bracket, square that. Which in turn is going to give me, so let's look at my denominator first. 1 minus omega squared LC quantity squared plus omega RC squared, square that whole thing. And then what's going to go on with my numerator? Well, it's just going to be the square of the numerator on the left plus the square of the numerator on the right. So that is nothing more than 1 minus omega squared LC quantity squared plus omega RC quantity squared. And it should hopefully be very obvious that my numerator is effectively the same thing as my denominator, but my denominator just has that squared, right? So if I cancel this guy, it's just going to take 1 power away there, leaving me with the relationship 1, excuse me, divided by the square root of 1 minus omega squared LC squared plus omega RC squared. So just as a sanity check, let's look at what this is going to look like at omega is equal to 0. So to me, my numerator is obviously 1. My denominator, I'm going to have 1 minus 0 squared, which is just 1, plus 0 squared. So 1 over the square root of 1 is 1. So we pass all of our extremely low frequency signals. And then when we're looking at infinity, I have one minus infinity squared, so that's going to be negative infinity squared. Square that would be positive infinity to the 4th power, whatever that means. And then I'm taking the square root of that thing. So it's going to be 1 over infinity squared, which looks like approximately 0. So we pass low frequency signals, we attenuate high frequency signals, exactly like what we would expect of a low pass filter. Because this is a second order filter, we're going to have a resonant frequency omega naught, still nothing more than 1 over square root of LC. That'll be true of all of these because it's just a series RLC circuit. However, this does not represent our 3 decibel cutoff frequency. So our 3 decibel cutoff frequency, let's call this omega C, is going to be given by the following expression. And this is going to be large and gross, and I'm not remotely deriving it. As a matter of fact, I just got it using MathCAD by setting my transfer function equal to 1 over square root of 2, and then just having it symbolically solve it for me because I got sick of doing algebra. So this is going to look like the square root of r squared c quantity squared minus 4 r squared LC plus 8 L squared. All of this is divided by twice L squared C quantity squared. Outside of that square root sign, we have 0.5 r squared C minus L divided by L squared C, close brackets, and then putting this to the 1/2 because I didn't want to put another square root sign in there. Everybody knows that raising it to the power of 1/2 is the same thing as taking the square root. So this is our -3 decibel cutoff. So it is not intuitively obvious as to why our cutoff frequency isn't something like our resonant frequency, right? So when we were looking at the bandpass filters and the bandstop filters, everything worked out reasonably okay, or at least it looks similar to something that we had seen before. We have this odd looking thing, and it's because we have to take into account what's called resonance, which we'll go into in much more detail in circuits 3. But effectively, what we can sometimes see, and it depends on the values that we choose for R, L, and C, is that the maximum value of our transfer function won't necessarily be 1. It might be larger than 1 in regions very, very close to our resonant frequency. And then it's not going to fall down 3 decibels from that maximum value until we hit this frequency. And because where that peak value falls depends so much on the different configurations of components is why we get such a gross looking expression for our cutoff frequency. So it will be somewhere near the resonant frequency, but typically a little bit later. So a little bit higher frequency than our resonant frequency, because what we may see would be something like this. Okay. So this would be our magnitude response of h of omega. Here's omega. So let me do what we would expect to see for a first order circuit would be something like this. May make this a little bit less steep. For a second order circuit, we might see something that looks like this. So it'll be the same flat thing, but then it might rise up like so. And the steepness of how quickly it rises up there is what's called the quality factor. Again, this is something that we'll talk about in much greater detail in circuits 3 before it falls off at a much steeper rate of change because it's a second order filter as opposed to a first order filter. And our 3 dB cutoff frequency is measured from this peak point. So a little bit different behavior, again, depending on whether our system effectively looks kind of like it's underdamped in frequencies close to the resonant frequency, which causes that brief oscillation before falling back down. All right. So lastly, we have our phase response. So as per usual, excuse me, this will be nothing more than the inverse tangent of the imaginary part over the real part. So that's going to look like negative omega RC over 1 minus omega squared LC squared plus omega RC squared divided by 1 minus omega squared LC divided by that exact same denominator, 1 minus omega squared LC squared plus omega RC squared. Which comes out to be the inverse tangent of negative omega RC over 1 minus omega squared LC. All right. So last thing that we wanted to talk about, or that I wanted to talk about with regards to filters, would be looking at a second order high pass filter. So similar question to what we saw earlier. What element do you expect me to be taking the voltage drop over? The inductor, absolutely right. So here we'll have our resistance R, our capacitance 1 over J omega C. And our inductance J omega L. Here's V out as a function of omega. And somebody other than Patrick, since he did the last one, tell me what our transfer function here should look like. Okay, I'm on board with that. So I'm going to simplify this by multiplying by negative J omega C over negative J omega C. You may be asking yourself why I happen to choose a negative sign out in front here, and it's simply so that my numerator isn't negative. Right, so J times J is -1, so I threw an extra negative sign in there to make my numerator a positive quantity. So continuing on from here, our numerator is going to look like omega squared LC. And then our denominator I'm going to have a minus J omega RC as my imaginary part. And then I'm going to have a omega squared LC minus 1 as my real part. And much like we did in the previous example, I'm just going to multiply this by the complex conjugate of the denominator over the complex conjugate of the denominator. So that would be omega squared LC minus 1 plus J omega RC over omega squared LC minus 1 plus J omega RC, which gives us omega squared LC times omega squared LC minus 1 as the numerator of our real part. And then it'll look like omega squared LC times omega RC as the numerator of our imaginary part. Our denominator is omega squared LC minus 1 squared plus omega RC squared. And that's true for both the real and the imaginary parts, which is why I'm allowed to split it up like I do. So our magnitude response, as always, is just the square of the real part plus the square of the imaginary part, and then we take the square root of that whole thing. So I'm going to have omega squared LC times omega squared LC minus 1. Omega squared LC minus 1 squared plus omega RC squared. Close that and square it. Coming over here, omega squared LC omega RC squared. Sorry, should not be a squared on that. Race, there we go. Omega squared LC minus 1 squared plus omega RC squared. Square this whole thing. And that gives us, we'll do the denominator first. Omega squared LC minus 1 squared plus omega RC squared. Square that whole thing. In our numerator, so hopefully it's fairly obvious that there's an omega squared LC squared coming from the left-hand portion, and there's an omega squared LC squared coming from the right-hand portion. So I'm just going to factor that out from both sides. So I have a common factor of omega squared LC squared. The left-hand side is going to contribute an omega squared LC minus 1 squared. And the right-hand side is going to contribute an omega RC squared. And so I hope very obviously, this guy right here cancels out one of those powers, leaving us with omega squared LC divided by the square root of omega squared LC minus 1 squared plus omega RC squared. Yes. So that it's of the exact same form that I've always had. Something in the denominator, either the number one or a simple expression in terms of omega with no square root, and my denominator is always the square root of a combination there. Absolutely right. So at very low frequencies, the numerator is just going to look like zero, so it's zero. I guess technically it does matter to look and make sure the denominator isn't also going to look like zero. But it should be fairly obvious that we're going to have 0 minus 1 squared. So that's going to look like -1 squared or +1. So 0 over 1 is 0. At very high frequencies, we are going to have omega squared in the numerator. So that's infinity squared. In the denominator, we're going to have the square root of infinity squared squared. So we have infinity squared over infinity squared is effectively 1, and we get the exact high pass response that we would be expecting. Our resonant frequency is simply the square root of 1 over LC. And our 3 decibel cutoff frequency is going to be extremely similar, but not quite exactly what we saw for our low pass filter. Okay. So we'll have the square root of R squared C quantity squared minus 4 R squared LC plus 8L squared divided by twice L squared C squared plus 0.5 R squared C minus L divided by L squared C. Let me close that square root sign, close this, square root that whole thing. So look back at your notes that we just did for the previous example and tell me what the difference is. That sign, that's it. Everything else is literally identical, just the sign on that second part changed. Let's see if contextually that makes sense. So if we look over here for our 3 decibel cutoff frequency for this kind of graph, it's going to be slightly after the resonant frequency, right? Well, if we had this graph effectively flipped around, we would expect to see our resonant frequency, or excuse me, the 3 dB cutoff slightly before the resonant frequency, which is why that sign was changed. It's literally going to be the exact same thing, but it's going to be just as far to the left of the resonant frequency as our 3 dB cutoff frequency is to the right of the resonant frequency in a low pass filter. So all of these things are related. All right, lastly, we have theta as a function of omega is the inverse tangent, and I'm just going to skip ahead here. Negative omega RC over, hold on, let's see. Oh, we're doing the high pass filter. Positive omega RC over omega squared LC -1. Yes.
Are these like constant formulas for this type of circuit or just?
So these for a series, so for a filter made from a series RLC circuit, which would be a voltage waveform filter, it's true regardless of what type we have. Yeah. So we didn't specify any particular value of R, L, and C, so this will always work. Now, let me ask you a slightly different question because I did clarify just there that these are for voltage filters. Why did we use a series RLC circuit and never look at a parallel RLC circuit? Yeah, so a parallel RLC circuit in parallel with a voltage source means the output voltage is always the exact same thing as the input voltage. But if we put a current on the inside, a current as our signal source, then it's going to filter different frequencies of current. So for a simple voltage waveform filter, it's always going to be a series combination like this. At least for first and second order filters. Getting into Chebyshev and elliptical filters and all of that kind of stuff, it's just going to look kind of like a ladder network, I guess you would call it. So it's going to be a combination of things. So just as a quick aside, it would be something like, here's our input, and then we might have some type of impedance here, could be resistor, capacitor, inductor. And then another impedance. So this would be typical of, I believe, a Chebyshev filter. And then we could stack on further of those little blocks effectively. So if we wanted to put another one of these, that's just making it a higher order filter and so on and so forth. And depending on where we put the capacitors and where we put the inductors, it'll either be a high pass filter or a low pass filter. I'm trying to remember exactly what you do. Oh, for band pass and band stop filters, instead of this being either a single capacitor or inductor, it's a combination. But that's a circuits 3 problem. We'll go through all that kind of stuff later on. All right. What do you guys want to know about the test other than exactly what's going to be on it? Go for it. That is correct. So you are allowed to have a formula sheet for this test. 1 page, standard 8.5 by 11 sheet of paper. So no legal paper, no roll of butcher's paper that's 70 feet long or something asinine like that. Handwritten, cannot be a print off or anything like that. The reason why I want it handwritten is so that one good student doesn't do a hell of a job of making a great equation sheet and then distribute it to the entire class, because I've definitely had that happen before and it pisses me off. So everyone was responsible for their own equation sheet. I don't have anything in particular that you're not allowed to put on it. So if you want to put worked out example problems and all of that kind of stuff, you're totally free to do that. I have definitely had students before who literally put not a single equation on their equation sheet. They just wrote down all the dumb shit that I had said that quarter and then brought that with them to the test just to make fun of me. They still made their A. Totally fine. So I will collect your equation sheet with your exam, or I will instruct the proctor to collect your equation sheet with your exam. But with regards to what goes on there, as long as it's handwritten, I'm okay. I haven't seen anybody do this, but like, don't try to write stuff so tiny that you need a magnifying glass or an external source to be able to read things. I've also heard, don't know whether or not these are just true or urban legends, of people writing stuff in red ink and then in blue ink and then using those shitty 3D glasses to be able to look like effectively getting twice as much information as on there. Honestly, I don't know realistically, for the take-home portion, or excuse me, for the in-class portion of this test, if you have S is equal to VI conjugate is equal to P plus JQ, or S angle theta S, and then you have power factor is equal to P over magnitude of S is equal to cosine of theta S. That, you literally need nothing more than that, in my opinion. Everything else can be derived from that in 1 to 2 steps. If you want to put more stuff, that's up to you. Realistically, that's literally all you should need. Oh, and I guess the equation for capacitance, because that would be annoying to derive. P old tangent theta old minus tangent theta new omega voltage drop across the capacitor magnitude squared. Make sure you have those. Everything past that is fluff as far as I'm concerned. Correct. Again, I don't think you need it. You can put everything you need on literally a 3x5 note card, but I will allow you to spend as much time writing an equation sheet as you want, because writing down the relationships, example problems, and all of that kind of stuff is a good way to study. So I'll let you put as much crap as you want on there, but I honestly think that would get you through this test quite easily. Yes.
I know you don't care about not just one this year. You said there will be what's the capacitance value?
There will definitely be a power factor correction problem, so calculating the value of a capacitance, but that would be one part of a multi-step problem. So, fantastic that my memory is hot garbage, so I can't remember literally what I put on the test. But a circuit where you have, I don't know, some voltage source, maybe a transmission line impedance, and then, you know, so ZW, load 1, load 2 kind of thing, where, I don't know, maybe I give you this voltage drop at the loads, might be the voltage itself, might only be the magnitude or something like that. Something like that, I would ask you, like, hey, what's the complex power absorbed by load 1? Part B, what's the complex power absorbed by load 2? Part C, what's the complex power absorbed by the transmission line network? Part D, what's the total complex power supplied by the source? Part E, what size capacitor would be needed to correct the power factor of the source to some target kind of thing. That's the type of power factor correction question you should expect. So it'll be part of a larger thing, and yeah, like getting that right isn't going to be, 30% of the grade or anything like that. It'll be 6 points or something. So just to be clear, steady state sinusoidal circuit analysis. So, circuits, I might give you a circuit in the time domain. I would expect you to convert it into the frequency domain, perform analysis on it in the frequency domain, and then spit the answers out in the time domain, similar to what you did in circuits 1 and on at least one homework in this class. Power analysis, steady state sinusoidal power analysis, so complex power related stuff, which is what all this jazz up here is. Maybe an effective value problem. So I give you a waveform or a mathematical function, and I expect you to be able to compute the effective value of that. That's the kind of stuff that you should expect on the test, on the in-class portion of the test. Take-home portion will be where multi-frequency and all that kind of stuff pops up, because there's just not enough time to fiddle through all that in an hour and 15 minutes. So
So the in-class portion of this upcoming test is very similar to what you guys saw on exam 3 in circuits 1, except that partial credit is a thing. So if anything, it should be significantly easier than what you had in circuits 1. Any other questions? All right, do you guys on? Yes. There will be a bonus problem. The bonus problem will be based on filters, and it will be literally just, I give you a simple circuit and you hit me with a transfer function. You don't have to simplify it unless you particularly feel like it. So my expectation is literally what Patrick and Ethan, right? Yeah, did, sorry, brain fart. Like that part right there is as far as you need to go to get full credit. The design project. Yeah. No, I need to push that back because I haven't assigned it to you, or I don't think I put the. Yeah. Why don't you guys shoot me an email about that? Yeah. Yeah. So, remind me and I will get that posted, but realistically, the design project for filters should be way easier to do than the design project for op amps because you just have equations to apply. All right. See you guys on Monday because I won't be here on Friday.